Hello, Professor Hildebrandt here. Again, I'm working some calculations of probability from our textbook in Chapter 5. This corresponds to the second part of my lecture, and we are, on these examples, I'm going to focus on our two rules of multiplication. And our probability rules of multiplication are used when we have events that are occurring at the same time. They occur simultaneously. So for my first example, I'm going to use what's called the special rule of multiplication, and this is for events that are independent of one another. So this means that event A occurring has no effect on whether or not the probability that event B will occur. Okay, so let's suppose we have a tire company, and they have found that the probability that their tires will last at least 60,000 miles to be 0.95. Now, as a customer, I'm going in and I don't need just one tire. I need a new set of tires. So I'm going to purchase 4 tires. And so I might want to know the probability that all 4 of the tires that I purchase from this company will last at least 60,000 miles. And so to do this, I will use the special rule of multiplication. And in this special rule of multiplication, you simply take the probability that A will happen, so the probability that A happens, and we multiply that times the probability that B happens, and times the probability that C, and so on and so forth for however many events we have. And for this one, the probability for all the tires is the same at the 0.95. So to find my overall probability here, I'll just take 0.95 and multiply it out 4 times, once for each tire. Again, it's independent, so whether or not my right front tire makes it 60,000 has no effect on whether my back left makes it 60,000. When I multiply all of these out, then we get a probability of 0.8145 that all 4 of the tires that I have purchased are going to make it at least 60,000 miles. And so again, when events are independent of each other, we use the special rule of multiplication. So for my second example, I'm going to use something where we have to use what's called the general rule of multiplication, because this time my events do depend on each other. So there's the dependence, or we say there's a conditional probability, okay? Conditional probability. And what the conditional probability means, because there is a dependence here, the value is going to be conditional on what occurs in our first event. So whatever occurs in event 1 will impact what event 2 can be, will impact what event 3 can be, so on and so forth. So let's add an actual example with numbers to try to put this in all together for you. So we have a board of a company, and this board is comprised of 12 individuals, 8 are men, and 4 are women, okay? And our company is searching for a new president, and so we're going to randomly select a committee of 4-member, so 4-person committee, out of the existing board members to find us a new president. And so perhaps I want to know, well, if we randomly select from our existing board, what's the probability that all 4 individuals selected would be women, or that all 4 individuals selected would be men? And so now this is a little bit different than the last rule of multiplication, because now there is a dependence on each other here. So let's start with all women. So for my first event, the first person randomly selected, the likelihood that it will be a woman is 4 out of 12. Where does this come from? Well, because there's, again, 4 possible women to randomly select from out of our total board, which is comprised of 12 people. So there's a 4 in 12 chance that the first person selected would be a woman. Well, what about the probability for the selection of the second member of my committee? Well, if, because again, we're looking for all 4 to be women, so if a woman was selected with the first drawing, then there's only 3 women left to pull out of a total of 11. If a woman is selected for the second position, then now for the third position, there's only 2 women left to potentially select from out of a total of 10. And then for the last one, there's only 1 woman left to select of the remaining 9. And if we multiply this out, we see that the odds of this particular board having a 4-member committee that are all women to be a very, very low probability of 0, 0, 2. Now, looking at the makeup of the board, if we want to see that the chances that they would be all men, we'll use the same process. But just looking at the composition of this board, I can already estimate, hopefully you can as well, that more likely the probability is going to be higher here that all 4 committee members would be men, because there are twice as many men serving on this board as they are women. But let's do the math and figure it out. So what's the probability that the first committee member selected will be a man? Well, there's 8 men total sitting on our board of 12, so there's an 8 in 12 chance. If there is a man selected for spot number 1, that only leaves 7 out of the remaining 11 to be selected from. And if a man is selected again, we're left with 6 of 10. And then lastly here, 5 of 9. When I multiply this out, I get a probability that my committee would be all men to be 0.1414. And so for an application of this, if we were hoping to have a diversity in this 4-person committee that's going to select our new president, but we still wanted to randomly select that committee so that we didn't have any personal biases in terms of which board members would be on the committee, well, then there's a fairly good chance we will have at least some men and some women serving on this 4-person board, because again, the probability that all would be women is extremely low, almost 0, right, at 0.002. And the probability that it would be all men is also still very low at 0.1414. So I hope this helps some with using these rules of multiplication.